Welcome to lesson 3.4. Today we're going to cover the rational root theorem, which is going to allow us to sketch the graphs of polynomials. So we've already seen the integral zero theorem, and the integral zero theorem only works when the leading coefficient is equal to 1. So if I have a polynomial where the leading coefficient isn't 1, one of the things we had talked about before was maybe if we're lucky, there's a common factor and we can common factor out that leading coefficient. If that's not the case, then we need to move to the rational root theorem. And the rational root theorem allows me to factor any polynomial when the leading coefficient isn't 1. So what the rational root theorem tells us is that as long as I have integer coefficients, I'm going to look at p, where p is any factor of the constant term, and q, where q is any factor of the leading coefficient. There can exist, and can is the really important word here, rational roots of the function such that p of the quotient p divided by q could equal 0. So if I can find values of p and find values of q where that creates the function to be equal to 0, then I know that I found a factor of that function. Once I found a factor of a higher degree polynomial, I'll be able to use synthetic division to divide and then eventually factor the function. And then I should be able to find all the roots, and then I can start to sketch it from there. So I'm going to start by looking at factoring this quadratic, and then we'll show that the rational root theorem would work with this quadratic as well. So if I'm going to factor it, I'm looking for factors of 8 times 15. So I want factors of 120 that add to 22. And I have to be a little careful with my signs there. You might notice right away, since we're trying to add to 22, that the factors of negative 10 and negative 12 are going to add to negative 22, but give me a product of a positive 120. We haven't done any decomposition yet this year, so why don't we do this one through decomposition? If you wanted to just do it with inspection, you could do that as well. So I'm going to break up that negative 22 into negative 10x and negative 12x. In the first two terms, I have a factor of 2x that's in common, so that leaves me 4x minus 5. In the second two terms, I have a factor of negative 3 that's in common, which again leaves me 4x plus 5. That tells me I've done things correctly. I factor out the 4x. Sorry, I said 4x plus 5. That should be 4x minus 5. I'll just fix that. So I've got my 4x minus 5. I've got 2x minus 3. And so that's going to give me, if I'm looking for roots here, we'll set f of x equal to 0. So I get 4x equals 5. So x is equal to 5/4. And I'm going to get 2x minus 3 is equal to 0. I just sort of skipped the equal to 0 part in that first one. I'll go back and add that in just 1 second. That's going to give me x is 3/2. So I had 4x minus 5 is equal to 0. Okay, so now I factored it and I found the roots. Let's think about what happens with the rational root function. So if we just jump back up here for a second, we can see that p is a factor of the constant term. That means my values for p are 1, 3, 5, and 15. So when I'm looking at that, I'm doing 1 and 15 and then 3 and 5. My values for q are, so I'm looking at 8, so I'm going to have 1, 2, 4, and 8. Now, of course, if I want to look at the factors of 8 or the factors of 15, I could have plus or minus any of those factors, right? Positive 1 times positive 15 gives me positive 15, but negative 1 times negative 15 gives me positive 15 as well. Now, what the what the theory tells us is that the quotient P divided by Q are the values we want to try in big P in our polynomial to see if this works. So what I'm looking at, the way we often write this, is if I'm looking at P divided by Q, it could be plus or minus 1 or 3 or 5 or 15 divided by 1 or 2 or 4 or 8. So that means the values I'd have to check would be 1 divided by 1, 1 divided by 2, 1 divided by 4, 1 divided by 8, and then negative 1 divided by everything in the denominator. And then I'd have to do 3 divided by 1, 3 divided by 2, 3 divided by 4, 3 divided by 8, and then all the negatives, and then 5 divided by 1, 5 divided by 2, and so on, and then all the negatives, and then 15 divided by everything in the denominator. So there's lots of factors that I have to check here. When I do these, I'm going to focus. We can see they're not going to work for this particular example, but I'm going to focus on looking at nice values. So I would probably start by looking at the one in the denominator. So I would check something like, if I'm looking for a factor, I would probably start by checking what do I get if I do just P of 1. And if I do P of 1, so that's 1 divided by 1, either positive 1 divided by positive 1 or negative 1 divided by negative 1. And I go to evaluate that. So my function was 8x squared minus 22x plus 15. And so we can see that P of 1 is equal to, what do we have? Is equal to 1. So 1 is not a root, right? That doesn't work. We can get rid of that. I could, if I was doing this sort of from scratch and I wasn't able to factor it, I would just keep going through and evaluating different values. Since I can cheat a little bit here, I'm going to, since we were able to factor it, since it was a quadratic. I'm going to evaluate P of 5/4. Now, everything that we know tells us that P of 5/4 better be equal to 0 because it's supposed to be a factor. So I'm going to get 8 times 5/4 squared minus 22 times 5/4 plus 15. Okay. Well, so let's see, that's going to give me 25 times 8 over 16. We'll reduce that in just a second. The 22 over 4, I'm going to reduce that to 11 over 2. So that's 11 over 2. I still have that 5 in the numerator, and then I've got a 15. So I can reduce the 8 over 16 to a half. So I've got 25 over 2 minus 55 over 2. And I can rewrite that as 30 over 2, right, to get myself a common denominator so I can add things together. And lo and behold, we see that P of 5/4 is equal to 0, right? 25 plus 30 gives me 55 over 2, minus 55 over 2 gives me 0. I can run through really quickly and just check P of 3 over 2 as well, just to prove that it's going to be a factor. Now, as I'm doing this, the thing that's really important for us to remember that I have already mentioned is that if I didn't already know which values work, I would have to just be trying values to find a factor. And when we have higher degree polynomials, that's what we have to do. We have to use the rational root theorem to find a whole bunch of potential factors, and then we use the rational root theorem to see which one of them is going to actually work. And then I can use synthetic division, and I can start to divide to get the function down to something that I can factor. Okay, so I can see that the 2 squared is going to cancel with the 4 and the 8, so that leaves me with 2 times 9 minus 33 plus 15. So 18 plus 15 gives me 33 minus 33. And again, we can see that that gives us a factor there. I wouldn't not jump to those two factors overly early. I would try with, I'd start with 1 and -1 and 3 and -3 and 5 and -5 and 15 and -15. And I would work through that process and realize that none of those were factors. And then I'd probably start dividing by 2. So I'd find that root at x equals 3 over 2 a lot faster than I'd find the root at x equals 5 over 4. What we're going to do now is we're going to look at a cubic that we can't factor, and we're going to use the rational root theorem to find the roots of this function. So that means the values that I'm going to try. So if I look at P over Q, it's going to be plus or minus, so the factors of 27 are going to be 1, 3, 9, and 27. So I'm just breaking it down into the factors in my head as I go. 1 times 27, 3 times 9. We just did 8, so it's 1, 2, 4, and 8. And then I just have to start trying that function, right? So I need to start trying values. Again, I'm going to start with a 1 in the denominator. So I'm going to try f of 1. All I have to do is find a function. I don't need to find I just need to find a root. I don't need a whole bunch of roots, and I'll show you why in just a second. So if I put in x equals 1, I get 8 minus 12 minus 18 plus 27. So that gives me f of 1 is equal to 5. So that's useless. So let's try f of -1. So if I do f of -1, I'm going to get -8 minus 12 plus 18 plus 27. So I get minus 20 plus 45. So f of -1 is equal to 25. So that's no good. So let's try f of 3. So f of 3, and I mean, if you want to, you can just do this in your calculator. You don't necessarily need to, do this all by hand. I've been doing it by hand, but there's no necessarily a reason to. So I'm going to have 8 times 3 cubed minus 12 times 3 squared minus 18 times 3 plus 27. That gives me 81, so that's no good. So now I'll try f of -3. And so that'll give me negative, right? Because a negative value cubed is going to give me a negative value. So I'm just sort of skipping half of a step there. Minus 12 times 3. Sorry, that should be -3. Minus 18 times -3 plus 27. That gives me -99, so that's no good. So now I'm going to try f of 9. And so I get 8 times 9 cubed minus 12 times 9 squared minus 18 times 9 plus 27. That gives me a massive number. So then, what do I got? 4,000. I think it was 725. Okay, so now I'm going to try f of -9. And so this procedure just has to keep going until we get a factor here. So I'm kind of hoping that some of you are going to recognize that there's a shortcut here, especially if we have a graphing calculator at our fingertips. Now, the problem is we're not always going to have a graphing calculator at our fingertips. So then we have to think about what's happening. Now, I should have brackets there, but let's get those in. Okay, there we go. In terms of sort of ways we can make this go faster when we're working at home, we have a graphing calculator in front of us. I could use the graphing calculator and I could just put the equation in y equals form. So we're doing the same thing that we looked at the other day again. So minus 12x squared minus 18x plus 27. And so if I look at that data table, I don't see any functions, or sorry, any roots right away. So maybe what that wants to make me do, and I'm just going to change my table so I can do this, is I know that after I go through all the ones on the bottom, then I'm going to go through a whole bunch of stuff that's at a half. And if I do that, oh, wrong button, there we go, on the table, I can see that at negative 1.5, I have a 0. And at 1.5, I have a 0. So let's check those, right? Instead of doing the 27, just in the idea of trying to save ourselves a little bit of time. So let's try f of 1.5, or f of 3 over 2. We'll do it as 3 over 2. Okay. So that gives me, let's just do it in the calculator. We'll show that it works. So 8 times 3 over 2 cubed minus 12 times 3 over 2 minus 18 times 3 over 2 plus 27. And that gives me, oh, I got a 9. Why did I get a 9? Oh, I forgot to square my x on my negative 12 there. So we'll throw a square in there, and then we need to insert subtraction sign, and now we're good. And we can see that that is equal to 0. So my options now, I want to divide that function. We'll just write it out again. I want to take that function and I want to divide it by 3x minus 2. Right, that 3x minus 2, well, maybe there's an easier way to do that. Oh, I said I had 3x minus 2. It should have been 2x minus 3. Just gives me that point. So if I'm going to do this with fractions in synthetic division, let's take a look at how this is going to work. So we know the 8 comes down. 8 times 3 over 2 is going to be 12. I add those together, that gets me a 0. 0 times 3 over 2 is 0. That gives me a negative 18. Multiply 3 over 2 by negative 18, and that's going to give me negative 27. And look at that, I get a remainder of 0. So what I end up with is f of x divided by x minus 3 over 2 is going to be 8x squared minus 0 x minus 18. Okay. So what that tells me then, just going to sort of put a line over here. What I know now is that f of x is equal to 8x squared minus 18 times x minus 3 over 2. Now, I have an option here. I can use rational root again. I mean, it's going to be a bit of a pain because, again, I still have pretty big numbers for my leading coefficient and for my constant. Or I can use factoring methods that I already know. So if I look at that trinomial there, I'm going to factor out a 2. That's going to leave me with 4x squared minus 9. And then I had my x minus 3 over 2. Now, a lot of the time, what's going to happen here is I might multiply that 2 back into the second set of brackets, so I'd get 2x minus 3. Doesn't matter if we do or not. Hopefully, we recognize that we have the difference of perfect squares happening here. And so I get factors of 2x minus 3 and 2x plus 3. And then I still had my factor of x minus 3 over 2. That gives me all of my factors. You can see that I'm going to get a few more factors there of 3 over 2 if I go through and solve it. I want to take a quick look in Desmos and graph that for us. So just one moment. Okay, so you can see I've got the function graphed for us here in Desmos. I haven't zoomed out so we can see all the behavior of the function, but we can see that the end behavior matches what we would expect for a cubic. And I can see that I have roots at negative 3 over 2 and positive 3 over 2, or negative 1.5 and positive 1.5. Something special going on here because we can see that the vertex is actually sitting on the line, and we're going to talk about that in a couple more minutes. Okay, so when it comes to dealing with polynomials, what's often going to happen is we're going to get something that can be factored using some of the factoring methods we already know. Rational root theorem is great, but as we've just seen, it can take a while to find where one of those roots is, which will then allow us to start working our way down through the function and get it into something that we already know how to factor. That means we need to be able to factor. So in addition to some of the factoring we've already looked at, one of the things that's probably new to us this year is the sum and difference of cubes. And sum and difference of cubes looks very, very similar to what we saw with sum and difference of perfect squares. And the thing that's really important to know about factoring something that has the sum and difference of perfect cubes is that the factors, just go back here a little bit. Got to get the A in there first. One of the factors, or the binomial factor, is going to look like ax minus b. A lot of times we might not have the a term there. We tend to have, just the x, or if you're looking online, you might see it just as like x cubed minus a cubed, or x cubed minus b cubed. But if I think about what has to happen in order to have the square terms and the linear terms cancel out, I can actually figure out what the trinomial is going to look like here. So the leading term, in order to get a cubed x cubed, that has to be a squared x squared. So when I multiply my ax by my a squared x squared, I get the a cubed x cubed. The final term inside the brackets here in this trinomial has to be a b squared. So when I multiply my b squared by my negative b, it gives me my negative b cubed. That also tells me that that's a positive sign. So now I need to get some cross terms to cancel out. And so thinking about some of the cross terms that are going to come up, I'm going to have negative b times a squared x squared, and I'm going to have b squared times ax b squared. So maybe if I want to think about getting that negative b times ax or a squared x squared to cancel, I know then that the middle term is going to look like negative b, or sorry, positive b times ax. Now I think the easiest way to do this is to run through a check. And so I'm going to go through and I'll multiply the ax by all three terms first, and we'll see how things are going to cancel. It's going all the way over to the b squared. So I'll get a cubed x cubed, and then I'm going to get plus b a squared x squared, and then I multiply the ax by the b squared. So that gives me a plus b squared ax. And then I need to do the negative b's. So I'm going to have three more terms here. So I'm going to get negative b. Oh, look what's happening. A squared x squared. That's going to cancel with that term. And then I'm going to get negative b squared ax as I multiply the negative b by the positive bax. And that's going to cancel. And then the last term that I'm left with is negative b times b squared, which gives me negative b cubed. And so I can see that I get back to the original starting point where I have the difference of perfect cubes. Now, if I look at the sum of perfect cubes, it's the same idea, but we're just going to have some sign differences. So I'm going to have an ax plus b as my binomial factor. And then inside the brackets, sort of following the same thought process we had before, we're going to have an a squared x squared to give me my initial term, or my first term, my leading term there. I need to end it in a positive b squared. And then in the middle, I'm going to have some signs that are going to, like I need a negative sign to get things to cancel. And so that middle term this time is going to be negative bax. And so if I do my check, I'll start with, I'm just going to switch colors this time for the check. So ax times a squared x squared is going to give me a cubed x cubed. That's the term we want to keep. Ax times negative bax gives me negative b a squared x squared. Ax times positive b squared gives me b squared times ax. B times a squared x squared gives me b times a squared x squared. And I can see that those two terms are canceling out. If I keep going, I'm then going to have b times negative b ax, which is going to give me a negative. B times b gives me the b squared, the ax. I can see that those terms are going to cancel out. And then I'm left with b times b squared, which gives me a plus b cubed. And you can see that I'm back to where I started before I started to try and factor that. And I get a cubed x cubed plus b cubed. So that's sum and difference of perfect cubes. It's not maybe something that you need to memorize, but if you remember that the difference of perfect cubes has the sort of cube root of the first term minus the cube root of the last term, which is similar to what you would expect from perfect cubes by comparing it to the difference of perfect squares, I think you'll be able to find your way through those factoring processes. Other things we can do, we can factor a quartic as a trinomial, and we've done this actually way back in grade 10. So I'm just going to do this with a little substitution. We didn't always do this with a substitution in grade 10, but we'll see how we can do this. If I let z equal x squared, that turns this fourth degree polynomial into something that's a second degree in z. So I get z squared minus 5z plus 6. I can factor that, so I'm going to get z minus 2 and z minus 3. Now I can substitute back in for z, so that gives me x squared minus 2 and x squared minus 3. So those are the factors. Let's say I was looking for the roots. I'd get x squared is equal to 2, so x is equal to plus or minus root 2. And then I could do the same thing with the other one. So if x squared minus 3 is equal to 0, I'd get x squared is equal to 3. So x is equal to plus or minus root 3. Last thing for factoring, we took a quick look at this a little while ago. A little bit of factoring by grouping. So in this one, I look at the first two terms, and the second two terms, I have an x squared common in those first two. So that leaves me with an x plus 3. There's a negative 1 common in the next two. That leaves me with an x plus 3. And so I pull out that common factor of x plus 3, and then I have x squared minus 1. And I can further factor that cubic. So I can get a beautifully factored cubic at this place by recognizing that I have the difference of perfect squares there in my x squared minus 1, and there's my fully factored cubic. So these factoring methods that we've seen before in the past are going to come back, and they're going to help us as we deal with higher degree polynomials. So the point of really everything we've done in Chapter 3 is looking at the equations and the graphs of those polynomials. The one thing that we have left to look at is what's called multiplicity, and this is when we have repeated roots. So when a polynomial has factors that are repeated so many times, it is said to have a multiplicity of whatever that degree is. So if I look at the polynomial that I have drawn down below, you can see that the factor at x equals 2 repeats 3 times, and the factor at x equals negative 1 repeats 2 times. So for this polynomial, we would say that it has a multiplicity of degree 3 at x equals 2 and a multiplicity of degree 2 at x equals negative 1. Now, with multiplicities, I've graphed the polynomial for us here. It tells us about what happens when we reach the root. If I have an even multiplicity at that root, then I'm going to have a vertex at that point. So the function does not change signs. If I have an odd multiplicity, then the function changes signs at the 0. So the function, we can see that happens right here at that x equals 2 point, right? It has a multiplicity of 3, so the function's going to change signs, which means it's just going to pass through the 0 and going to continue. So I can sketch any nth degree polynomial by hand by factoring my polynomial, looking at the end behavior, calculating both x and y intercepts, again, maximums and minimums, and then points of inflections, which we may not even be overly sure about at this point, have to wait until calculus. Okay, so in this example, we are going to sketch the following polynomial without using our graphing calculator. So that means we're going to have to think about the end behavior. We're going to have to factor it to find our x-intercepts. We can find our y-intercept, and then we can go through and sketch it. The first thing that I'm going to notice is that there's a common factor there. And so to make my life a little bit easier, I can actually pull a factor of 2 out of all of the terms. So that's going to leave me with 4x to the 4th minus 7x cubed plus 6x squared plus 32x minus 32. Now that leaves me in terms of the factors that I need to check. because I've been able to factor out that 2, I don't have to worry about dividing by anything. And so that leaves me with plus or minus 1 and 32, 2 and 16, and 4 and 8. So I'm just going to, we'll start at y of 1. We'll see if 1 happens to be a root of this. So I'm going to get 2 times, so 1 to the 4th is 1, minus 7 plus 6. The nice thing about this is it's just all the coefficients, right? That's why we like ones. And I can see, so my 32s cancel, and then I get 1 plus 6 is 7, minus 7 gives me 0. So that tells me that x minus 1 is a root. So I need to divide, I need to take y and I need to divide it by x minus 1. So I'm going to do that using synthetic division. So I'm going to put my 1 in the box, and then I get, so I don't have to worry about the 2 there, right? It's just the polynomial that's inside my brackets that I need to factor. And it'll just be a factor of 2 in front of it. So my coefficients go 1, negative 7, plus 6, plus 32, minus 32. Now, our sort of built-in check along the way here is that if I do this correctly, I know, because this point should be a root, that I should have a remainder of 0. Okay, so I multiply 1 by 1. Negative 7 plus 1 gives me negative 6. Multiply through, that gives me a negative 6. Add those together, it gives me a 0. That gives me a 32. 32 times 1 is 32. And look at that, we can see that our remainder is 0. So I'm just going to call it y. Divided by x minus 1 is equal to x cubed minus 6x squared. There's no x term, and then I have a plus 32. If you want to put in like plus 0x, that's, you know, you're more than welcome to do that, and it'll help us sort of remember exactly what's happening. Now, I'm using this to factor. So what I have done so far is I have rewritten okay, there we go. I've rewritten my function y so it looks like this, right? So I've taken the x to the 4th minus 7x cubed plus 6x squared plus 32x minus 32, and I factored that to be x minus 1 times x cubed minus 6x squared plus 32. We can always run through and double check that by multiplying the binomial by the trinomial there, or I guess it's not really a trinomial, but by the cubic function, if we really wanted to see what was happening. So now what I need to do to keep going is I need to factor this thing. So I'm just going to call it, just to give it another name, I'm going to call it h of x. And so as we apply the rational root theorem, we can look at the factors of h of x. So I've got x cubed minus 6x squared plus 32. So I still have to factor and go through and check. I still have factors of 32 is what I meant to say there. So I still have to go through and check plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, and 32. So there's all my factors of 32. Looking at it this time, I can see that 1's not going to work. It definitely isn't going to happen. And thinking a little bit about what's going on, because I have that big constant, I'm probably going to need some negative terms. So let's try h of negative 2, right? If I want to be able to cancel that out, I'm going to have some things that are going to subtract. So negative 2 cubed is negative 8. 6 times negative 4 squared, well, negative 4 squared, we're doing negative 2. Negative 2 squared is 4. That gives me negative 24 plus 32, and we can see that x equals negative 2 is also a root. So that tells me that a factor of that cubic is going to be, I want to take h of x and I want to divide it by x plus 2. So I'll do my synthetic division over here. I'm dividing by -2. My cubic coefficient is 1. My squared coefficient is 6. And the one we have to make sure we don't forget about, the linear, or the coefficient on just the x, is 0, and then we get a 32. Again, as I divide through, I know that I should get a remainder of 0. So -2 times 1 is -2. Add those together, that gives me -8. -2 times -8 gives me 16. 0 plus 16 is 16. And there we go. -2 times 16 is going to give me -32. Leaves me with a remainder of 0. So that tells me I've rewritten h of x as x plus 2 times x squared minus 8x plus 16. Well, if we look at that, that looks like one of our factoring shortcuts. And I have the sum of perfect squares there. And so I've got x plus 2. I can factor x squared minus 8x plus 16 as x minus 4 times x minus 4, or x minus 4 squared. And now I should have my complete function completely factored. So what I have, I can say that y is equal to, I'll start off with these terms. I'll put the 2 in there because we know there's going to be a 2. So then I'll grab the terms from the h of x. Okay, and then if we slide back up, remember that's what we called h of x. I still need to have that factor of x minus 1. Now I'm not going to do it here. Oops. But one of the things that we could do if we wanted to is to expand out that the function that we have here to check that we end up with, way back up at the top, the 2x to the 4th minus 14x cubed plus 12x squared plus 64x minus 64. So if we go through and we multiply all that together, we will see that we have that same function. And I'm gonna actually write that full thing down. So all right, minus 7x cubed plus, I think it was 6x. Oh, no, okay, so it should be a 14, 12, and then 64. So let me just fix that. So 14x cubed plus 12x, and then I had 64x, and I just can't remember what those signs were, so I'll jump back up and then fix them. I guess I could have pretty easily looked at my just multiplying these together. I'm going to get a positive 2. When I square that, that becomes a positive 16. And so that gives me positive 32 times negative 1 gives me negative 32. And then I have my coefficient in the front. So that gives me my sign on my constant term. So what do we know about the, well, let's do the y-intercept. There's a nice easy one. We've got all of our x-intercepts, but for our y-intercept, we can see that it's going to be at 0 and negative 64. If I want to know about the end behavior, so for my end behavior, I'm looking at the fact that I have a positive sign in front of the leading coefficient, and I have an even function. So that tells me as x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to negative infinity. So I I should be ready to sketch this at this point. I've got all my roots. Now, I haven't explicitly written out my roots. I still have it in factored form, but I have all my roots, and I have my y-intercept, and I have my n behavior. So if I take a look at what this graph should look like, I'm going to have one root at -2. I'm going to have a double root at +4. So that tells me there's going to be a vertex there because I have a multiplicity of 2 at that point. So there's my point at 4. I have another one at x equals 1. So that's at 1 and 0. The function starts. Let's add our y-intercept. So this is not anything close to being to scale here, but it'll give us an idea of what the function looks like. So I've got 0 and -64 as my y-intercept. Okay, so the function comes from infinity. We're going to come down somewhere down here. That looks pretty ugly. Let me try that again. Somewhere down here, we're going to have a minimum. I don't actually know if it's where x is negative or x is positive. And that doesn't really matter to us right now. Now, we'll get this to come up. We know that we're going to have a vertex sitting on the axis at x equals 4 because we have a multiplicity of 2 at that point. And so the function does not change signs. Now, if I just very quickly grab my calculator and we'll graph the function. So I've got 2x to the 4th minus 14x cubed. I missed a square there. That should be 12x squared. Just fix that, and then we'll go back to the calculator. Plus 12x squared plus 64x minus 64. Now, if I look at sort of my window settings here, I know that in y at least, I'm going to need to go pretty far down to be able to see that. So I'm just going to extend that graph down. It doesn't look horrible, but maybe we'll extend that graph up a whole bunch as well too, so we can see what's happening. So that looks pretty good. We can see that, on the graph when it's done to scale, that minimum that we have down here looks like it's maybe a little further down, but we don't know how to find that minimum or how to find that maximum at this point. We do have our vertex sitting right on the point at x equals 4, and so we have a pretty decent sketch of our function. Let's just run back up here to the top of this example and think about what we've done. We took the function, we started by finding the x-intercept. So we started to factor the function. First thing I did is I pulled out a common factor because we know that's always our first step in factoring. I used the rational root theorem to look at the factors that I should be checking. Found that x equals 1 is a root. So that tells me, I said root here. I should really say that x minus 1 is a factor. Because x equals 1 is my root. I take y, I divide it by x minus 1. Means my a is 1, so the a is the value that goes into the box. I do synthetic division, I get a cubic. So I have a partially factored function y now. I grab the cubic that I still need to factor. I'm going to call it h of x just to make life a little bit easier. I look at it, I realize that I'm going to need a negative value. -1 doesn't work, so I try -2, and I see that -2 ends up being a root as well. So the factor, if -2 is the root, the factor is x plus 2. A is -2. I use synthetic division again, and I divide. I get a factored form of h of x. Then I have a quadratic. I can factor that quadratic by hand very quickly. It's just some perfect squares. pull the whole thing back together as the factored form. The factored form gives me the roots. The expanded form gives me my y-intercept. I look at the coefficient in front of the leading term or the term of the highest degree to understand the end behavior. And so I can see that as the function goes either off to the left to negative infinity or as it goes off to the right as x goes to infinity, the function's going to approach infinity. I think I said this right earlier, but I wrote a negative sign in there for some reason. That should have said that y approaches infinity in both cases. And that's how we drew it. I draw my axis. I label my three roots. I recognize because I have a multiplicity of 2 at x equals 4, I'm going to have a vertex sitting on the axis at that point. I also label my y-intercept. I have the end behavior, and that gives me an idea or a rough sketch of the graph. I can't figure out exactly where those maximums and minimums are because that's a calculus problem. All right, so that is how we apply everything we know about factoring and the rational root theorem to be able to sketch higher order polynomials.